Okay, so I'm going to start. So first things first, welcome back. We left speaking about, when I was talking about, just to be sure, can you hear me right now? Just move a hand if you, okay, good, thanks. Okay, I thought, so I'll just take a little bit of a detour to come back to something I said, and I feel like maybe I should have been more precise. I was talking about how in the Kaluza-Klein part of the lecture, how these series of exceptional groups that aren't really exceptional up to n equal to 6, like SL5 for n equal to 4, how they are contained symmetries and then symmetries manifest upon Kaluza-Klein. For instance, SL5 contains some GL4 times a bunch of translations. The translations are shifts of the treeform. When you put all the legs of the treeform along the internal space, you could do something similar for type 2B. But I thought maybe I should be explicit in showing how you can see this at the level of the algebra, and then show you how this works also in the O10, 10 case, just so that we are sure that we all understand each other. So what I meant by that is the following. So SL5 as an algebra has the adjoint representation, which is 24 dimensional. That's just 5 squared minus 1, because the determinant is fixed. And you may break it with respect to a GL4 subgroup. So when you do that, you get this decomposition. 4 minus 3 plus the adjoint of GL4, which is a singlet for the determinant, and the 15, which is 4 squared minus 1, it's the adjoint of SL4, plus 4 prime plus 3. Okay, so this is GL4 as an algebra. And these are the shifts of a treeform on T4. We are going from 11 to 7 dimensions. So the torus is a 4-dimensional torus. Now, why is it a 4 prime? Well, if you have a 4-dimensional manifold, you can use the Levi-Civita symbol, which has 4 indices, to rewrite this into some Cn upstairs. That's why it's a 4 prime. The charge under GL1 is what it is. It is the charge of an object with 3 indices downstairs. So that's plus 3. Some people have opposite conventions. They flip 4 and 4 prime, and they flip the charges from plus to minus, depending on preference. So you can see that there is a subalgebra, which is GL4 plus R4. We can even do it as matrices. The fundamental of SL5 is a 5 by 5 matrix. You can imagine as a group, actually, let's just do it directly as a group. So this will be our coset representative in block triangular form. You're going to have your Filbine with some prefactor here and some other factor down here, just because you want the determinant to be 1. Just deduce which powers of the determinant of the Filbine you need there. And then you're going to have 1, 2, 3, and 4 entries here reproducing this R4 and 0 down here. Okay, so that's how we embed GL4 times R4 inside SL5. And then these 4 entries here are going to be called CM. And I think now, probably, I think I flipped conventions, and that's actually, no, actually it's okay. I think this is fine. Yeah, sorry, fine. This is actually done. Oh, well. Let me not waste too much time on this. There is a CM and then I'll get in the wrong position for it. And so I will need to think it back. Let me do it for the ODD first. Or at least we had already written it down correctly. That's what happens when you try to well, let me just say, you can write it like this, and then I'll come back to the CM just to make sure I don't tell you something wrong and then I don't come back to it. So let me play something similar for O10, 10. What's the adjoint of this? That's 190 dimensional, 20 times 19 divided by 2. You divide it into 45 minus 2 plus the GL10, so that's 1 plus 99 plus 45, that's a prime, plus 2. And so you have your GL10, and here you have your B shifts. And so indeed, this was actually fine. Now I'm coming back to my senses. You just flatten the index with the field. Sorry about that. Just like in what we wrote in the first lecture for the B field. So again, you see the structure, okay? So these are the hidden symmetries. In terms, you might remember in the first lecture, I wrote the generators as a C here, a B, and then some A and minus A transpose. And B and C were antisymmetric. Then the B are the B shifts, the C are the hidden symmetries. Okay, in the case of O10, 10, we are not yet talking about symmetries because we need to look at how the coupling to derivatives are. But that's the structure you might think of. That's where your fields leave, but then O10, 10 contains more generators, of course. Okay. So that's just in case you're not used to this going between branching of representations and parameterization of a coset represented. Questions here? Okay, it wasn't too smooth, so questions will be more than understandable. Okay, so let's actually move back to double fit theory now. So we got to say that the fields of double fit theory, let me make a blank board, are parameterized in terms of some generalized metric, which I'm only going to write sketchingly now. Roughly of this form. And we did say, well, O10, 10 acts on these objects, just like you would expect, for instance, for Busher rules. But we haven't said anything about coordinate dependence yet. So there's something we can do now. We should remind ourselves that we have gauge symmetries for these fields. We have diffeomorphisms. So we could take our coordinates, the actual coordinates for now, these are just the coordinates, 10-dimensional space and coordinates, going into x mu plus some vector. And then we know how this acts, like, so xi g mu is a transport term. Yeah. And then we have a rotation term, which is given by what? Well, I call it rotation, but it's general linear transformation. V mu xi rho Let me write it with a factor of 2 directly and symmetrization. Okay, this is transport. And this is, well, really, let me call it for what it is, GL10 action. Okay, I might call it rotation, but of course GL10 is more than rotations. Okay, where this is the GL10 matrix, the derivative of the vector of your infinitesimal change of coordinates. Okay, how does B transform? Well, actually, how does any field transform? As long as they are covariant, as long as they are tensors. L psi of some field phi is always going to be the transport term. Plus, let's put it this way. We compute big psi. This is an element of GL10. So we are going to write it using an index in the adjoint of GL10. And then the variation under GL10 of my field. If it is a tensor, then it must sit in some representation of GL10. So I can say this. This is just however phi transforms under GL10. Okay, and possibly perhaps it's a tensor density, and then there might be some weight times phi, which you may or may not want to include in what you mean by delta GL10. Okay, that's how everything transforms under change of coordinates, anything covariant at least. So this was breaking down, good. Then we have another transformation. The B field transforms under something I'm calling lambda, and Eric is going to call zeta, which is just its standard transformation under 1 for lambda mu. Okay, and the metric does not transform under that. Okay, so now we want to somehow encode these gauge parameters. What are the gauge parameters? We have psi, we have this lambda, into representation of O 10, 10. We would like everything to be in representations of O 10, 10. Well, that doesn't seem too hard, right? We have exactly what we need to define an object, which we may call a generalized vector, which contains exactly psi and lambda. Now, the fact that this has any sensible transformation property out under O 10, 10 is a completely different story. And we see where the catch is there. But we can definitely fill out a double vector using these two objects. And for now, that's enough. But then we get to the point where we face a problem, which is, what about derivatives? You might remember when we were doing this brief review of Kaluza-Klein reductions, I mentioned, you don't get hidden symmetries before Kaluza-Klein reduction because the vectors coming from the metric couple to derivatives, and you don't have a full R1 representation of derivatives. You only have as many as the internal directions, which are much less. That's because the R1 representation also covers charges associated to winding or to brain wrappings and so on. So how do we get rid of this issue here? Well, the solution we have is we actually double the coordinates. And that's where there's a little bit of philosophy, perhaps, that needs to be discussed here. if you do generalized geometry, if you prefer the language of generalized geometry, there is no doubling of coordinates there. All you may do is you may say something like the following. Well, my coordinates, my space-time coordinates are 10. I'm not going to change that. But I may somehow embed my d mu into some doubled object. It's just a little bit of a trick, meaning that I will write some object with an index capital M in the vector representation of all 10, 10. But I actually need to remind myself that what I really mean by this is that the first half are physical derivatives. The second half of the object is just 0. Okay, I could just do that. And in doing so, I could write down expressions that only involve dm, never look at what dm is. And as long as I don't look inside it, my expressions are going to look like they are O10, 10 covariant. Alternatively, I can do something a little bit less conservative, and that's how you usually have double and exceptional field theory presented. What you do is you actually extend the coordinate dependence of all your fields so that you have enough coordinates to cover the full R1 representation, the full vector representation here. So what does that mean? Of course, there's going to be a price to pay. But for now, we just do it as naively as possible. We just say that we in fact have a double amount of coordinates. Half of them are those that are familiar to us, but we add the other half. Morally, if you're doing a worship theory, that's not so bad. In a worship theory, you might say I add bosons, and bosons that you somehow, you try to write your worship theory in a way where momentum and winding are at the same footing. Okay, there are several formulations like that. We do it now at the level of supergravity, though, as a local field theory. There's going to be a catch somewhere, because clearly adding extra coordinates means adding more degrees of freedom that our supergravity theory has. So somewhere we will need to pay the price. But for now, we just do that. And then, of course, we have our set of derivatives, which are d by dx m. So for now, I'm just postulating this. Why am I doing it? Because I want to encode, in terms of these doubled vectors, these gauge symmetries here. But in order to do it in a form which is O10, 10 covariant, I have no other choice than to extend my derivatives from 10 to 20. Okay, so I'm doing it by, in fact, extending the whole coordinate dependence. So now we are going to do the following. We are going to forget about these gauge symmetries. We are just going to take an object called lambda capital M, assume it depends on these 20 coordinates. dm is the derivative, and we are going to postulate a set of transformations, a generalized version of a Lie derivative, okay? At the end of the day, once we look at what it is, we will come back to what I'm describing here to you. We will remind ourselves, actually, the structure of what we write will force us to remind ourselves that we don't actually have double number of coordinates after all. We reduce ourselves to the physical ones, and suddenly we found out that what we defined reproduces the correct gauge transformations. The reason we do it this way is that it is easier to understand the structure of this generalized Lie derivative if we just take it for what it is, forgetting the reason somehow we are trying to define it. It's easier to see how it works if you just take it at face value. Questions here? Okay. Maybe this is a little bit too big. I do need some space. So what we are going to define now is usually called generalized diffeomorphisms. So we have a parameter lambda m, which plays the role which in standard diffeomorphisms would have been just a vector extraction of the tangent bound. And for now, we just say it depends on my double coordinates, but I'm not going to write capital X all the time, just to learn. And now we need to, I want to define a generalized Lie derivative. And as you usually do, even just in general relativity, the easiest way is to define how it acts on another vector, in this case, another generalized vector. The first thing you expect is that it will need a transport term. So far, so good. Nothing new here. Then you probably expect something that looks like what we had for bad choice of letter. For a standard Lie derivative, if we were just doing 20-dimensional general relativity, this is what the Lie derivative would look like. Instead, that's not good with us, because at the end of the day, we know we want whatever this object is, we want it to act on things like the generalized metric, H. That satisfies some O10, 10 invariant identities. If we act on it with something like this, those identities won't be respected anymore. It will be rotated outside. It won't be an element of O10, 10 anymore. It's going to be a generic GL20 element instead. So we need to fix it. The way to fix it is we add an element similar to this. Actually, let me put it this way. Eta PQ, eta MN, dn lambda Q. Why do we do this? Well, because this expression here is an element, algebra element of SO10. So imagine acting on H. Lower. How is this going to be? Well, we definitely have the transport term, that's fine. And then we are gonna have this element here. Let me call it just parentheses. I'm not gonna write it again. Okay, this parenthesis is the whole expression you had in there. And this is symmetrization. This is how H transforms, just by O10, 10 covariance. Now you may check that the defining property HMM, actually HPQ of HMP, HNQ, eta PQ equal eta MN is preserved by this infinitesimal variation of H. Okay? And so far, the fact that I have somehow chosen to double my amount of coordinates is not doing any harm. So it almost feels like we managed to get a theory just from this idea of projecting standard rotation term that you would have in a derivative. By projecting it onto ISO 10,10, it almost feels like we are authorized to include double the coordinates you will use it having supergravity. And the extra ones might even have an interpretation as winding. So where is the catch? Well, the catch is these need to be symmetries. One of the important things about symmetries is that they close onto each other. If I apply two symmetries, I must still be getting a symmetry after all. So what happens when I require closure? Of the generalized derivative. Long story short, that forces you to restrict your coordinate dependence. But I want to actually see a little bit of how this happens. But questions up to here first. Any questions? Okay. So this is the starting point. This is the basic definition we need. There are a few different ways to proceed here. One of which is in the lecture notes. It takes a little while to do the whole computation, so I'm not sure how much of this I'm going to do, because I'd really like to start the exceptional part today. Of course, we still have an hour, but time can fly if you don't pay attention. So let me make a little bit of a choice here. I'm going to start the beginning of this, but then I'm going to skip several steps, okay? We are gonna need plenty of space. So let's start from scratch. I'll rewrite the general definition. A little bit smaller this time. In the meantime, if you think of any questions, don't hesitate. Okay. Now, what do I mean by closure? By closure, I mean that if I apply two symmetries, I must get another symmetry. So if I want, at the end of the day, to construct a theory invariant under these transformations as symmetries, they better close onto each other. They may as well close onto themselves plus other symmetries. Perhaps we have more symmetries than this, and then they're allowed to transform to close onto more of these symmetries. But we won't encounter that for now. If you start doing things like E8 exception field theory, that's actually what's going to happen. But here, these are all the symmetries we have. We need them to close onto each other. So what that means is, suppose I take the commutator of two derivatives acting on some vector. I'd really like this to be itself a generalized diffeomorphism. Okay, that's the statement. I apply two of these on lambda 3. I must be getting, this must be, again, a generalized diffeomorphism. We could actually require a little bit more, and I'll come back to that. But that's the least you can impose. Well, then all you have to do is start opening up stuff and trying to guess, well, what is lambda 4? Lambda 4 can depend on lambda 1, lambda 2, the derivative of lambda 1, derivatives in principle of lambda 2, but not on lambda 3. Okay, lambda 3 is just an object you act upon, but you want your symmetries to close onto themselves, not to be field dependent. Okay, lambda 3 might become any field in your theory. I just pick lambda 3 to make it easy to use the definition up here. You could call it V. Maybe I should have called it V, but it's called lambda 3 now. So we need to guess a lambda 4. And whatever we find, it needs to hold for any lambda 1, lambda 2, and lambda 2. So what we do is, I'll do the beginning so that you get an idea. And then in the exercise session, or you could do it by yourself, we keep going with this timing computation. But I want you to see at least the beginning. So the first thing we do is we just use the definition we were just looking at. That's perhaps a little bit boring. I'm just copying the first line, okay? Just changing a few names here and there. So I'm going to do the left-hand side first. So it's going to be what I just wrote minus the exchange of 1 and 2. Okay? And now you apply this again. Notice that there is only one free index. So I can apply the same definition, just calling what was V here, this whole expression. But I need to be careful with the derivatives, right? The first thing I get is some lambda 1 R, dr lambda 2 P, dP lambda 3n. That's this term when I act with lambda 1 dP on it. There's another one, no? This dr should also act on lambda 3, but thanks to anti-symmetrization, at the end of the day, that would cancel out, so I'm not going to write it. Now I want lambda 1 dP to act on this term. This time I need to get everything, dr lambda 3, dP lambda 2n. This time there is no anti-symmetrization saving me, so I need to write both terms. dr dP lambda 2. I hope that's reasonable for you. Do interrupt me if you can't read what's going on. Okay, now I need always this first term in my definition, acting on the last thing here, plus eta mn, eta pq, lambda 1r, dr dn lambda 2, q lambda 3p, and then something similar with the derivative acting on lambda 3, the dr derivative acting on lambda 3. And I'm sure you get the idea of how the rest of the computation will go for this first piece. 3p. So I'm just going to write plus dot dot dot. Let me see if I can write dot 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 here. Or there's anything else I need for my next statement. I think that's enough for the first statement I want to make. Okay, very good. So you get the idea, and at the end of the day, you did the minus exchange of 1 and 2. Okay, you can complete the expression. That's actually one of the exercises asked you to do a similar computation. That's exercise 6. I'll come to that. I'll comment on that if you don't have it at hand now. And the notes anywhere do contain, hopefully without typos, the full expression I'm not writing here. But for now, this is sufficient. The left-hand side contains other terms, but in particular, these ones. Now, the left-hand side, I can just write here. It's always the same thing. Eta PQ, dn lambda for Q, lambda 3P. Now, let me remind you of something. We said that this identity, this thing here, needs to hold for any lambda 1, any lambda 2, and any lambda 3. The only thing we can choose is lambda 4, and it cannot depend on lambda 3 anyway. So in particular, I may choose a lambda 3 that is 0, but whose first derivative is not 0. Okay, why will I do that? Well, because in doing so, the dot dot dots I didn't write won't contribute. And some of the terms I wrote also don't contribute. I can make a choice because functionally, the terms that depend on d lambda 3 are independent from the terms that depend on lambda 3. And so I'm going to fix only those terms that depend on d lambda 3. I have one here. Well, that's better. And then I have this one here. Right? For lambda 4, by making this choice, you're left with only this one. I'm getting confused about something. Give me a second. I think by writing dot 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 too early, I dropped a term I needed. Let me look back here. Right. So what's going to happen, and sorry, I'm going to cheat here, otherwise it takes too long, that this term actually won't contribute. Let me cross-check this again before I cause confusion. That's the risk of cutting short the computation when you hadn't planned to do so. So it will cancel out between the dot dot dots and the anti-symmetrization. But let me check this is actually what's going on before we keep going. That's good, yes. Other questions? I hear some noise. It wasn't intentional, okay. Okay, so drop this term because it will cancel out. Sorry about that. I chose to write dot 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 too early. You're left with this box here and this box here. So you may notice that, so actually this one I'll draw in blue so you don't get confused. Only look at the red stuff. This and this. That's not new, right? I have just been left with closure of a standard derivative. All the stuff that contained etas disappeared. Okay, because I'm setting lambda 3 to 0, and I'm saying I only take d lambda 3 terms. And because I'm not showing you how this cancelled out, because I'm cutting the computation short. So you may say, well, very good. It wasn't that bad. Lambda 4m is just what it is for a standard derivative. Lambda 1r dr, lambda 2m minus the anti-symmetrization in 1 and 2. So far, so good, very good. But now I need all the other terms when lambda 3 is non-zero. And that's where we will make things a little bit shorter than intended. One way to see why things might go wrong is to look at terms like this. So terms that depend on eta, right? That's the difference with respect to standard derivatives. So those terms will play a role. What it turns out happens is you just don't get closure. Okay, so these terms won't cancel out if you take lambda 4 to be the naive expression you expect for a standard generalized derivative, for a standard derivative. On the other hand, this was already the correct answer for that worked for all the terms proportional. So this works for d lambda 3 terms, right? Well, I didn't entirely show it to you because I didn't show that cancel out, but for the rest, hopefully you believe me. So if I want to change lambda 4, I need to make sure that whatever I add doesn't break the fact that everything was already working when I was looking only at d lambda 3 terms. And remember, lambda 4 cannot depend on lambda 3. So I cannot put some functional dependence on lambda 3 to make things work, like make lambda 4 plus some d lambda 3 term added inside just to fix things. So I am somehow stuck right now, okay? The reason I'm stuck is that I have a lambda 4 and dp lambda 3 enter in the right-hand side of my closure. And I know that lambda 4 has to be this expression for the d lambda 3 terms to cancel out. So the only solution you have is to hope that for some reason, I can shift lambda 4 to lambda 4 plus something else, lambda 4 tilde, such that lambda 4 tilde PDP of lambda 3, but lambda 3 is arbitrary, so really of anything must be 0. That's the only way, because otherwise I'm already stuck. But now we face a problem. If dp, if the internal derivatives are really all there and they're acting on an arbitrary object, that's a complete basis in 20 dimensions. There is nothing that contracted with them can give you 0. So we see the need to drop some of those coordinates. We see why generalized derivatives cannot possibly close if you keep all those 20 coordinates, all those double coordinates, okay? With a little bit more of detail, we could actually get to see what's the right constraint to impose, but I'm cutting this a bit short so that we can also get a break before the second part of the lecture. But at least this message needs to be clear. Closure will require some constraint on the coordinate dependence. Otherwise, you won't ever find a lambda 4 that gives you closure, no matter how complicated. So what is the final answer? This goes in terms of an exercise, but that not entirely. It turns out that the right thing to do is to impose a section constraint, or sometimes section condition, which is the following. Let me write down and then I'll just comment on this. We don't directly commit to saying, well, only my first half of coordinates are there and the other half are not there. We just state all my derivatives of any object in a theory. So in here, these blank spaces can be fields, products of fields, derivatives of fields, integrals of fields, it doesn't matter, anything, gauge parameters, whatever. It must always happen that this constraint is satisfied. Now, this is usually referred to as the strong constraint when the derivatives act on different objects. There is a weak version where both derivatives act on the same object, which again can be anything. If you do this, you immediately see that there are plenty of lambda tildes you could add to the lambda 4 we found. You could use something of the form eta dpq, dq of something, and any object like this will satisfy this condition. And the claim is, and I'm not going to show it to you to save on time, that you actually do find such a lambda 4. Exactly by shifting the expression I was giving you here, which was the naive one for a standardly derivative, by a lambda tilde of this, in this form. Okay? Now, clearly, we need to spend more time discussing the section constraint. And I'm going to do that after we take a break. Before we take the break, I'm going to mention exercise number 6, because it's a simpler way to convince yourself of why all of this makes sense. Although the reason I decided to go through this thing here you saw with this arbitrary lambda 4 that needs to be found is that it's important, if it's the first time you look at these things, it's important to convince yourself that certain loopholes, certain potential loopholes are not there, that you really need to impose such constraints, okay? So let me get to the exercise 6. And I'm gonna do it mentioning something more, which is a notion of covariance. So a generalized vector, Vn, is defined such that its transformation under a generalized diffeomorphism is the generalizedly derivative. That's not surprising, no? That's what you will do when you define a covariant tensor in general relativity. You say its variation under an infinitesimal change of coordinates is given by the Lie derivative in terms of the associated vector. But is the generalized Lie derivative of a vector also a generalized vector? So what happens if I compute d lambda 1 of L lambda 2 lambda 3m? Well, certainly is equal to the variation of the objects in my new derivative lambda 1, lambda 3. But now we know that this thing here is L lambda 1 of lambda 2. And this thing here is L lambda 1 of lambda 3m. And we would like to impose that the left-hand side is nothing but a Lie derivative. That's the request, that the generalized Lie derivative of a generalized vector is a generalized vector. Making such a requirement, we arrive at the Leibniz identity, the statement that the generalized Lie derivative is a derivation. Which I'm going to rewrite as in the exercise. The exercise asks you to check this using the section constraint, taking for granted the section constraint. Okay. It's a bit of algebra like the one you saw where I also got confused about the term and how it canceled out and ended up cutting it short. So it does take a little bit of time, but I think it's very instructive. The advantage here is you don't have to guess anything. There's no lambda 4 that you need to guess. Okay. Okay, this is a good time to take a little break. And if you have questions, you are more than welcome. Let's go back. Let's talk about the section constraint. I didn't entirely prove to you that this is what you need to impose for generalized Lie derivatives to close, but at least I hope I convinced you that there has to be a constraint on these dm for closure to be even possible, okay? And the claim is when you do things accurately, that's what you get. And we also said these Ds need to act on the same or on different objects, and these objects can be anything. Okay, so eventually these are really an algebraic constraint. What does it mean that it is algebraic? It means that really, I'm writing in terms of derivatives, but then that means that there's a constraint on the coordinate dependence of my objects. Really, these objects need to be some matrix times some index, and let me make up a silly name for this index, like, I don't know, psi, something silly, times d by dy psi, where these are dx psi, where these are actual physical derivatives. Okay? And such that this constant matrix satisfies eta mn en equals en equals 0. So that's what it means. It's an algebraic requirement on having a matrix, on saying that a bunch of, let me put it this way, that means that dn we'll have some entries which are actual derivatives, and then there need to be a bunch of zeros. It could be like this. It could be a little bit like this. It doesn't matter. Well, it does matter, as you have to solve the section constraint. But what is important is that this is an algebraic requirement. Okay, eventually you have fewer derivatives than the full DM. Okay, there are many ways you could write it down, as long as you understand it is not a differential constraint. It's really an algebraic one. But then maybe it's worth looking at what eta is after all, right? So eta is the metric of op 10, 10. So what we are saying here is that, let me make a little, well, yeah, let me write it here. Dn, if you think of them just as vectors, okay, just as algebraic objects, not as derivatives of something, span possibly maximally isotropic subspace of R20, right? There are all the non-zero elements of GM, all the linearly independent ones, the derivatives of any field, of any parameter, they must all anyway sit in the same isotropic subspace, such that their contraction with eta, even if you pick two different objects, still gives you zero. Okay, so when you translate it in terms of coordinate dependence, it means that your fields depend on maximally 10 coordinates, because that's the maximal dimension of an isotropic subspace for eta. For instance, the obvious choice, you could say that out of all the xm, only the original coordinates are there. And I write zero here, but what I mean is all the fields depend on x mu, but not on those extra x tildes I was introducing just to fill up the vector representation. This is better stated in terms of derivatives. It means that your derivatives of any field or any parameter are really the physical derivatives that were there to begin with, and nothing else. The rest is just zero. If you look at the expression for eta mn, which was of this form in 10 by 10 blocks, you immediately convince yourself of this. Okay? But there are other choices. You could drop these and only keep the second ones. That would be equally fine. You could do a little bit of one, a little bit of the other. But for now, let's just write this. So the important statement now is how many solutions can we find? And of course, you see, the point of what we wrote was that all our expressions were covariant under O 10, 10. They looked covariant. The only thing that's going to break our choice of O 10, 10 covariance is that we need to choose a solution of this section constraint. Once you pick that solution, clearly, this expression here on the right-hand side is not covariant under O 10, 10. A generic O 10, 10 transformation is going to map these first and half of entries into the second one, turning on the zero to something different from zero. But how many solutions do we have? Well, the answer is really up to O10,10 action. This is the only one. The only maximal one is the one we started with. So if you find any solution on the section constraint, so any section, or let's be more precise, any maximal, you could think of dropping more coordinate dependence than you need, making perhaps everything depend on one coordinate only. That's also fine, probably. But any maximal, that's what's most interesting section, is equivalent to this up to rigid O10, 10. So now you'll feel like we made a lot of effort to derive this section constraint. And at the end of the day, what we gain is that we are going back to our original Schwarz sector of supergravity. But that was somehow by design. So now we have our fields parameterizing some ODD covariant metric. There's also a dilaton, which I kind of ignored. One can define, in fact, an object, which is called D, usually, which is all 10,10 invariant, just from the Busher rules. That's how you find the Busher rules for the dilaton. And the gauge parameters are given by this lambda m. And the only other ingredient that shows up in my theory are dm on section. Is this my original Schwarz sector of 10-dimensional supergravity? Well, I haven't written an action for you in terms of these objects. But even before the action, you may want to check this. On section, taking dm to be the original set of coordinates, L lambda of h gives you back D fields and B field gauge transformations. So the way we formulated the generalized derivative is such that at the end of the day, it is actually correct to interpret lambda m as an object encoding diffeomorphisms and gauge transformation for the two form when you are on section. Now, what happens if I make a different choice of section? Like I pick the second half of the derivatives and not the first one, or perhaps just a mixture, right? I just multiply dm, this dm here on the board by some random O10,10 elements, a constant one. Do I still have such an interpretation? Well, not in terms of how I wrote h in the first hour, but certainly if I also apply the same O10,10 constant element to h itself, then they will cancel out. So if I rotate my section and at the same time I rotate my fields by the same constant O10,10 elements, it's like nothing happened, and I still get a parameterization of generalized metric such that generalized diffeomorphisms act as diffeos and B2 transformations. So that's the best we can do as long as the section is maximal. How can we convince ourselves of this? Well, what are the residual O10,10 transformations on section. We want some element of O10, 10. Let me write the derivative with that matrix I was defining earlier. Now that's the standard choice of section. Let's just pick the standard one, it's easier, okay? What kind of matrices preserve the structure here? They don't need to preserve each derivative separately, but what kind of transformations don't turn on the other half of the derivatives? Well, they need to be block triangular, right? There will be some G here, G inverse transpose here, and some B here, and a 0 here in 10 by 10 blocks. You apply this to this expression. What do you get? You get that you are rotating your derivatives, but you're never turning on the lower block. So you are preserving section. What is this group? Rather unsurprisingly, it's a group of reparametrizations of your spacetime and shifts of the two forms. GL10 here is a constant transformation. How do you get, is this a symmetry of material? Yes, it's just a special case of a change of coordinates. Just like in the Kaluza-Klein part earlier this morning, we said, oh, I shift Y by something linear in Y, and then I get a constant action on my fields. And then again, the same for R45, there's just constant shifts of the B field. Those are obviously a subset of the gauge transformations of the B field. So that's all that's left. Unless I do a Kaluza-Klein reduction. What's a Kaluza-Klein reduction? Well, it means I drop more derivatives than I need to solve section. In this case, there will be some extra subgroup of O10, 10 that survives. So when I do a KKI reduction, there will be some O(n, n residual symmetry. I hope you can see this just from the discussion here. That's of course T-duality. Now you can interpret the action of this. This is an actual symmetry of your theory, and it is T-duality on the internal torus. By dropping more than half of the coordinates, okay? Questions? So why can I only now call this T-duality? Well, because now I'm dropping both, I'm taking my 10-dimensional space, I say my fields actually only live on a subspace, and I drop momentum along a certain internal torus. Supergravity doesn't have winding. The section constraint tells us we cannot turn on winding, and that would have been the other half of the coordinates we tried to introduce, but were forced to drop. Now we are also dropping some of the momenta. Suddenly we are dropping both momentum and winding on internal torus. So we are back to an ONN symmetric state. Somehow in the trivial way, by dropping all the dynamics along those directions. And that's what you can do in supergravity. So two more things. I need to say something about dynamics. This can be phrased in terms of, well, I want to rewrite the action for the Noble-Schwarz sector of supergravity. All I'm going to say here is that you can in fact write a Lagrangian, and now there are many L's in these lectures, so I'll call it Blackboard L, the Lagrangian of double field theory. this is going to be some factor of the dilaton, but the ODG one, the O10-10 invariant one, times some scalar curvature, which is the double field theory generalization of what you would call a Ricci scalar. Now, there are several ways to think of this. One will be, we introduce partial derivatives dm, could rewrite a connection, some generalized version of a Christoffel connection, and then construct a curvature out of it. The connection will be somehow related to generalized metric, and then perhaps we can write a curvature. You can go that route. It's certainly instructive, but there's no time to go there. So I won't do that. I will just posit that there is a certain expression that is invariant under generalized diffeomorphisms. I should say covariant. It's a scalar under generalized diffeomorphism. And I call it RDFT, just like the Ricci scalar is a scalar. And you may write it as a functional of the metric and its derivatives, right? This expression is everywhere in the literature. Just copy it here because it feels like it needs to be written at least once. And also because we will see something similar in exceptional field theory. Wednesday, clearly not today. So this will fall from heaven. Okay, there is no way you can see why this is the right choice. As long as you see that this thing only depends on my generalized metric and this dilaton, which I'm rewriting as an O10-10 invariant object. Details of the expression go beyond what we can discuss now. Oops. And I need more space for the last term.
Gianluca, you have about 10 minutes left.
Yes, I know, thanks. There is just an expression. You also get it on the lecture notes. No sense trying to decipher my handwriting if it's not clear to you right now. What matters is, this is a scalar. Scalars don't make Lagrangians. Scalar densities of the right weight do. That's because a scalar transforms with a transport term and nothing else. But a transport term is not a total derivative. So when you take a scalar and multiply it by an appropriate scalar density of weight 1, the generalized coordinate, the generalized differential transformation of this Lagrangian is a total internal derivative. And so you may say that this Lagrangian is invariant up to total derivatives. Okay? Then out of this, you deduce by Euler-Lagrange procedure your equations of motion. And one can prove, it was done in the literature quite some time ago, that this is actually nothing more and nothing less than the original NS Lagrangian I wrote for you. You might say, can I do an integration and write an action? Which the issue there is integration on, what should you do? Integrate on double space or only on the physical coordinates? If you do it on the physical coordinates, that's fine, but then you break out 10-10 covariance. If you try to do it on double space, it's not clear what integration is because it's not clear globally what the double space is supposed to be. Questions up to here? Okay. I'm quite a bit behind schedule. I'll say two things. One, I think, is going to be needed for Eric's lectures next week, so I don't think I can postpone. That's the notion of, there is another way to phrase the dynamics. I won't write that down, it will take too long, but I at least need to get to the notion of generalized torsion. And let's put a line there. So imagine I have a matrix with a spectator index with a dot and the index you will have on a generalized vector. But now this is a not 10, 10 element. You can think of this as a collection of 20 generalized vectors because there is an upper and index. And the dotted index is just a spectator, okay? It just so happens that altogether these vectors form a not 10, 10 matrix. But then that means I can use them as parameters in a generalized derivative. In fact, you can think of, you could dress any generalized vector and flatten, dot its index by dressing it with u or the inverse of u, right? So it makes sense to compute this quantity. And because u is invertible, whatever you compute, whatever u is, you'll always be able to call the right-hand side, as I'm doing now, in terms of some coefficients t times, again, u. I have done nothing here. U is invertible. Whatever I have, I can just call it this way by multiplying with u inverse and then again with u. The important thing is that this is a rather crucial object called the generalized torsion. In particular, this is a scalar under Gen differ. And you're asked to show this in one of the exercises. It's actually not that complicated. Keeping in mind that the M index is a spectator here. Okay, that's why it won't be complicated. You can, in fact, using the fact that U is a no 10-10 matrix, there is an expression for this. You lower and raise indices with the eta, with the O10-10 invariant. I hope that's not confusing. dp u, that's the inverse, r dot. I wrote the eta explicitly here because I don't want it to be too confusing. So another exercise asks you from this expression here to derive this one here. And finally, there is a very well known U that shows up in double field theory, right? We said that H was some VV transpose, right? Where V, the coset representative, was exactly some object with the structure of this U matrix. So you may construct a generalized torsion associated to your fields. And when you do that, I'm not going to write it again because I'm really, really late. I'll do it here, cheating a lot. I'm sorry about this. You just change the name of U to V, and the associated generalized torsion you call a generalized flux. The reason I'm mentioning this is that you may rewrite the Lagrangian here, oops, there, just in terms of the generalized flux. There is a question, normally the torsion is 0. No, the generalized torsion is not 0. So it's not that the torsion is 0. In general relativity, you usually pick the choice of connection that gives you 0 torsion. You may pick a connection that does not have 0 torsion. In particular, the connection here will be generalized version of a Weizenburg connection, which is this expression you see here, just without antisymmetrization. You may want to check, I didn't want to put that as an exercise. You may want to check that if you construct an object like this without antisymmetrization, that transforms as a connection for generalized diffeomorphisms. But I didn't want to introduce connections for generalized diffeomorphisms. Okay? And definitely distortion is generally not zero. Okay. I'll try to speed through the very beginning of generalized diffeomorphisms beyond double field theory, but I think we will need more time clearly on Wednesday. So perhaps let me stop for questions first, because clearly we won't do much of that in any case. Okay. So one more exercise we might discuss tomorrow evening is to see that this generalized Lie derivative, once you are on the standard choice of section, reproduces the diffeomorphism gauge transformations of the true form. Right? You look at the generalized metric, this H, you act on it with generalized Lie derivative, and you see that you get the right set of gauge transformations, just giving the right name to the right object. Can we do something similar for the exceptional case? So what will be the equivalent of O10,10 for the exceptional case? So O10,10 is not a symmetry of the NSNS supergravity, unless you reduce to 0 dimensions, right? If you drop all the coordinate dependence. What's the equivalent of that for maximum supergravity? Well, that would be E11, which is, however, quite a monster of an object. And we really don't want to go there. So to avoid that, what we're going to do on Wednesday is to look at a dimensional split. Just as we did this morning, we will say, well, I consider now, I'm going to need some space. Right now, we were just at coordinate x mu, right? But now we go back to the situation in Kaluza-Klein, where we have our original coordinate x mu hat. We break them into some external and some internal p's. And then these parameterize some internal space of dimension n, let's say. If we dropped y dependence, that's Kaluza-Klein reduction, and we gain some ENN symmetry. And we ask ourselves, can we put all our fields into a generalized metric and a bunch of vectors and a bunch of stuff of other objects sitting in EN representations without actually having to drop the y dependence? And can we parameterize the gauge symmetries along the internal space in terms of the exceptional version of a generalized Lie derivative? And will we meet a section condition again? Yeah, we won't do that today. We'll do it on Wednesday, clearly. But the answer is yes, of course, to all these questions. In particular, the need to make things covariant will force us to extend the internal coordinates to some exceptional ones in a manner for exactly equivalent to what we did in this lecture. The only difference will be that this time we don't do it for all of them. We keep a piece of my 10 or 11 dimensional spacetime to be external and untouched, okay? And then we will indeed write down an L lambda, and the only thing I'm gonna write now is the structure of it, regardless of whether we are doing double or exceptional theory. The point of generalized diffeomorphisms is always that there's going to be generalized Lie derivative defined in terms of a transport term and then the projection of the derivative of my generalized vector onto the adjoint, onto the algebra, in this case of En instead of ODD, and then we act on our field. By how it transforms under En, and then there might be a density, just a rescaling piece. Okay, so what we will do on Wednesday is see how this very same structure also allows you to reproduce the gauge transformations along an internal space of 10 or 11-dimensional maximal supergravity, provided this dm here, again, satisfy a section constraint. And I'll stop because we are out of time.
Okay, let's thank Gianluca. Okay, and we reconvene at 5 after the coffee for rhetoric again.